Alright, so this is the video for section 10.3, which is all about the theory of equations. We have two main objectives that we're going to be looking at today. The first one is to identify all the zeros of a polynomial equation that involve multiplicity. So the big difference here is this idea of multiplicity is going to get involved when we haven't talked about that yet. The other objective is that by the end of this video you need to be able to write a polynomial equation when you're just given the zeros or the roots. So far we've worked really hard to try to find those zeros and the roots of polynomials equations. But at the same time, these solutions can occur more than once. So if an answer occurs more than once, that answer has multiplicity. Okay, so if the answer occurs more than once, when we say that answer has multiplicity. The multiplicity is based on how many times that answer really occurs. The multiplicity is based on how many times an answer occurs. So if we solved and we saw that that root or the solution or whatever you want to call it, if that occurs twice, then we say that the multiplicity is 2. If it were to occur 3 times, then we would say the multiplicity is 3. If it occurred 4 times, then the multiplicity would be 4, so on and so forth. If the root occurs more than once, then it should be counted more than once in our answer. I should say as an answer. Okay? And what I mean by that is we've been talking about this a lot, right? Where if the highest exponent is 3, then we should have 3 solutions. If the highest exponent is 4, then we should have 4 solutions. Now, if that answer occurs twice, it has a multiplicity of 2, then that answer gets counted twice towards those 3, 4, 5, 6, however many solutions we're expecting to find. And when we go to write our answer, we won't ever write the answer in our final line more than once. Instead, we're not going to write it twice, and instead of writing it twice, we just say the multiplicity, or we say the root has a multiplicity of 2, or whatever it happens to be. So let's pause there for a moment and just try that example that we see up here in the corner. So like before, the very first thing I would do is try to find my solutions. Before I find my solutions, I like to identify how many solutions I need to find. And since I look at this, my highest exponent is 2, which means my degree is 2, which means I need to have 2 solutions at the end because the degree is based on the highest exponent. So since my highest exponent is 2, my degree is 2, I need 2 solutions. So if I'm going to try to find these solutions, the first thing I would do is try to factor this because we have an x squared, an x term, and a constant. In this case, we can think about this as what multiplies to 9 and adds to -6, and that would be -3 and -3. So we have x minus 3 equals 0, which leads us to be able to say, okay, so that means that one of these has to equal 0 so that when they multiply together we get 0. So either x equals 3 or x equals 3. So again, we see that, hey look, that answer occurs twice. So since that answer occurs twice, we would say that my answer is 3 with a multiplicity of 2. And I know I've found all my answers because I needed 2 solutions, and my 2 solutions were 3 and 3. So since 3 happened twice, That multiplicity of 2 tells me that I found my 2 answers. And that's what I really mean by that. That when you're checking to see if you found all of the roots, you count the root as 2 occurrences or 2 solutions and not 1. Okay, because although we would think that there's only 1 solution and it's 3, that 1 solution occurs twice, which allows us to say that we've met the 2 solution requirement. This will help ensure that you have counted the correct number of roots. And remember, the number of roots should match. It should match the highest exponent in the polynomial. All right, so let's try a couple of examples with these. So let's look at example 1 down here. Again, the idea is we have to find the same number of roots by factoring in some sort of way. So in this case, when I look at example 1, my highest exponent is 3. So that tells me I'm going to need 3 solutions in the end because my highest exponent is 3. So I need to go ahead and try to factor this. Now in this case, I can't factor this the same way I did the top because there are 1, 2, 3, 4 terms. And since there are 4 terms, we're going to need to factor by grouping. So the idea is we would group the first 2 terms together, and we group the second 2 terms together, and make sure when you're grouping those second 2 terms together that that minus sign is like a negative that's stuck with the 4. So remember from first semester, we would look for a GCF. In this case, there's no number in common in the first set of parentheses, but there is an x in common. So my GCF is x, and we take the lowest exponent, which is 2. So now x squared times x would give me x to the third. X squared times positive 2 would give me the positive 2x squared. Then I can look at my second set of parentheses, and in here, there's a 4 in both of them, and since my first term is negative, I need to make my GCF negative. There's not a variable in both, so negative 4 is my GCF. Negative 4 times x would have given me negative 4x. Negative 4 times positive 2 would give me negative 8. Now I need to make sure at this point that the binomial and the parentheses match, and since they do, that tells me that this is factorable by grouping, and that my first set of parentheses comes from the GCFs, so that would be an x squared minus 4, and my second term comes from the other parentheses, so we have x plus 2 equals 0. Now, I would go ahead and try to factor this, right? As long as there's an exponent on it, we should try and factor it. Because this is an x squared, that's a perfect square. 4 is also a perfect square. They're having their differences, so we can go ahead and split them up. The root of x squared is x. The root of 4 is 2. And we have a positive and a negative, so that the middle term eliminates. We cannot factor this second binomial because there's no exponent on it, so we'll just bring it down. And then we can go ahead and set each piece equal to 0 to find what our roots or our solutions actually are. Which means we have x equals negative 2, x equals 2, and again, x equals negative 2. So we go to talk about what our roots are or our solutions or our zeros, because they all mean the same thing. I would say my solutions are 2 and negative 2 with a multiplicity of 2. And the reason why we need to confirm that is so we have one solution of 2, and then we have 2 solutions of negative 2, which matches the 3 solutions that we were supposed to have in total. Okay, so let's go ahead and look at example number 2. Now, example number 2 looks tricky at first, but remember, whenever you're factoring, you look for a GCF first. So in this case, when I go to factor, I see that there's a 4 and a 36, which tells me I have a GCF of 4. And then x to the 5th and x to the 3rd, so there's an x in common. The smallest exponent is 3. Now when I get to the end of this, I need to confirm that I have 5 solutions, because I will need 5 solutions since my highest exponent is 5. So my GCF is 4x to the 3rd. So I would need 2 more x's to get to x to the 5th, so we have an x squared. 4 times 9 would be 36, and we already have our x cubed, so I don't need to worry about that, equals 0. Now this time, when I go to try to split up this squared term, I'm not going to be able to, because although x squared is a perfect square and 9 is a perfect square, there's a plus sign between them, which means I cannot split them up. So instead I'm going to go straight to setting each piece equal to 0 and solving. So 4x cubed equals 0, x squared plus 9 equals 0, and then we would need to solve. So in this one we would divide by 4. So we would have x cubed equals 0. And then we would need to get rid of the cube by taking the cube root. So we would get that x equals 0. Now here's where you need to pause for a minute. When I look at this problem, okay, I see that this had an x cubed equal to 0. Well, because this is cubed, I should get 3 solutions from this setup alone. So when I get to my end answer and I end up with 0, I know that that looks like it's one solution, but because this was cubed and we took the cube root to get there, I know that this has a multiplicity of 3. So the answer of 0 occurs 3 times because of the exponent of 3 when I went to solve. All right, so now I'm going to go ahead and solve the other one. And again, this time there's an exponent of 2, so I should know that I'm going to get 2 solutions from this piece alone. So we would subtract our 9, and we would have x squared equals negative 9. And then we would take the square root to get rid of it, to get rid of that square. Now, remember, we're not normally allowed to take an even root of a negative number, so that means we really have to look at this as the square root of negative 1 and the square root of 9. Well, the square root of negative 1 would be I, and the square root of 9 is 3. And because this was an even root, we get 2 solutions, the positive and negative. So here we get x equals positive or negative 3. And this is 2 solutions because positive 3i is one answer and negative 3i is the other answer. So that gives me 2 solutions here. And I have 3 solutions on this side because 0 had a multiplicity of 3 as an answer. So I ended up with all 5 solutions. So my final answer is positive or negative 3i and 0 multiplicity 3. Now, number 3 looks confusing, but what I would tell you is when you're starting to look at this problem, you should realize they've already factored it for you, which actually makes this problem a whole lot easier. They're saying right here that we should get 2 solutions. We should get 2 solutions from this problem, right? And we should get 5 solutions from this second one. So it's already factored, which tells me that this one I can set equal to 0 and solve, and this one I can set equal to 0 and solve. So we would have x minus 3 squared equals 0. And in this case, it's important that you bring that square along, right? Because when we go to solve this, we're going to have to deal with this exponent. The other ones did not have exponents on the outside. Since this one has the exponent on the outside, the exponents need to come down with us when we set the piece equal to 0. So then we would also have x plus 4 to the 5th power equals 0. And we would solve each one of these separately. So on the first one, we need to get rid of the square by taking the square root. Well, the square root of 0 is just 0. Normally we would say it's positive or negative because it's an even root, an even exponent that we're taking an even root of. So we need to remember that we have the positive or negative here. Unfortunately, 0 doesn't have a positive or negative, so I can just say that it's 0, but I need to remember that then there's 2 zeros as a solution for that piece. And we're left with x minus 3. Then we can go ahead and add 3 to both sides, and we get x equals 3, and I know that this has a multiplicity of 2, because that 0 would have happened twice because of the exponent of 2. So I know my x equals 3 has a multiplicity of 2. Then I need to go ahead and look at the next one. This one's going to have a multiplicity of 5 because of that exponent of 5. So I'm going to take the fifth root of both sides, and the fifth root of 0 is just 0. So we have x plus 4 equals 0. We would subtract 4 and get x equals negative 4 with a multiplicity of 5 because this solution occurs 5 times based on that exponent. So 2 plus 5 gives me the 7 solutions that I would end up needing in total. So then I would just go ahead and write my final answer as being 3 multiplicity 2 and negative 4 multiplicity 5. And the next page will be on the next video.